following talk is an extended version of a presentation that I gave on June 13, 2015 at the University of Helsinki at the TSC 2015, that is, the Tour de Science and Consciousness Conference.
I can't remember when I first learned to count. I was quite young. Perhaps it was my parents or my brother who taught me. But from that early age, counting became easy. However, cognitively, counting is not easy to explain, and that will be the topic of my talk, trying to account for counting. In this talk, I will discuss, first of all, two pre-symbolic systems of numeration, the object tracking system and the approximate number system. These provide a background to exploring theories of counting, and I will particularly explore Carey's theory, which involves bootstrapping. I'll explore the bootstrapping metaphor a bit further, and then I will apply Carey's theory beyond the counting of natural numbers to the conceptualization of imaginary numbers, and in the end I will summarize what we've learned. How many objects can the mind embrace at once? That question was formulated by Sir William Hamilton in the middle of the 19th century. He conferred with fellow philosophers and he asserted that the answer was 6. William Jevons ran the experiment about a decade later. He did this by taking a handful of uniform black beans, anywhere from 3 to 15, and tossed them repeatedly into a round paper box and estimated or counted the number of beans that he perceived. He did this more than 1,000 times, and he concluded that at the moment when the beans came to rest, their number was estimated without the least hesitation. My conclusion is that the number 5 is beyond perfect discrimination. Now, as crude as this experiment was, his result is robust, and it stands to be pretty much the result that much more elaborate and sophisticated experiments would return today. By 1949, a name had been given to this phenomenon. It was called subitizing by Kaufman and his associates. This phenomenon of subitizing was explored from the 50s into the 80s on numerous occasions. A typical result is that of Mandler and Shibo, and you can see here where a reaction time is plotted in seconds on the vertical axis and the count size or the array size on the horizontal axis, that there is a markedly different slope once one ranges past 4, that in fact the reaction time increases progressively upwards beyond that point. The subitizing region remains somewhere between 3 and 4. The question then became how to account for subitizing behavior. In the early 80s, Kahneman and Treisman formulated the concept of object file, and related to that was an object token, which was seen to be an episodic representation of a real-world object. So a small number of objects would have a small number of tokens, and these would comprise the object file. Later in that decade, Filiushin came up with a related idea, the fingers of instantiation, FINST. The idea is that we have cognitive pointers, up to 4 of them, that track objects moving through the visual field. Now, FINST is primarily a spatiotemporal stored information. The concepts of object file and FINST coalesced into the object tracking system, or OTS, by the start of the 1990s. Now, the signature of the OTS includes its limited capacity. Infants can visually perceive from 1 to 3 objects and track them simultaneously. Adults typically 1 to 4 objects. They can discriminate these objects precisely and equally. Now, the information is primarily visual spatial, but there is a role played by the OTS both in auditory and in tactile discrimination. should be emphasized that the OTS is not a number system, that it represents tokens rather than numerical values. The evidence for the OTS comes from a variety of directions. There is developmental evidence that shows that the OTS is acquired up to an almost adult level by the infant by the time the infant is half of a year old. There is a neural location associated with the OTS. It's the right temporal parietal junction, and that is the region associated with visual attention. Comparative studies, both cross-culturally and cross-species, indicate that the OTS is present uniformly in human cultures, and that it ranges across species from whales to primates to birds. The second pre-symbolic system of numeration is the ANS, the approximate number system. It's also known as the analog magnitude system, AMS, and it is sometimes referred to loosely as the number sense. Now, the signatures of the ANS are the following. It is not limited by set size as the OTS with its limitation from 1 to 4. ANS runs from 1 onward. However, the representations are not precise. They are noisy. They are approximate. They follow Weber's law, and they give evidence in 2 different effects, the distance effect and the size effect. The representations are not only numerical, but also spatial length and area, also sound and tactile representations display ANS behavior. The ANS supports ordinal relations, magnitude judgments such as more or less comparisons. It supports approximate addition and approximate subtraction. There is also a variety of evidence for the ANS from the developmental side. The acuity associated with the ANS behavior increases with age. This is displayed by the lowering, reduction of the Weber fraction throughout childhood into adult years. The neural region associated with the ANS is well known and quite commonly studied. It's the horizontal part of the intraparietal sulcus. Again, comparative studies both across culture and across species attribute the ANS behavior to many different human cultures. The acuity, however, is found to be subject to both the individual culture and the education experiences of people in that culture. There is also a very wide cross-species evidence for the ANS. Here is just a partial list of some of the species for which the ANS behavior has been attributed. While studying the multimodal nature of the ANS, DeN and his associates have found that there is a consistent relationship between spatial and numerical representations. He's called this the SNARC effect, spatial numerical association of response codes. And in a loose sense, he says this formulates a mental number line. There is something going on here that's beyond simply a metaphorical number line. The evidence for the SNARC effect comes from several directions. There is behavioral evidence. There is association between not only between number and space, but number and temporal duration. The SNARC effect is found developmentally from infants to adults. The neural location seems to be the intraparietal sulcus and the prefrontal cortex, both of which seem to be involved. And from comparative evidence, the SNARC effect can be found not only in humans, but in macaque monkey studies. The N understands the snark effect as an integration of separate perceptual dimensions, but a complementary perspective by Walsh sees it from a different light. He's formulated a theory of magnitude that has been further developed by Lorenko and her associates. The idea there is that instead of having separate dimensions that integrate, that in fact there is a single generalized magnitude system that differentiates over time. They cite evidence from cross-magnitude interactions and from correlations in precision between numerical and non-numerical representations, and the fact that you can train and transfer information across different magnitude representations. Again, the issue is primarily a perspective of whether you see an integration of separate representations or a progressive differentiation of those representations. To briefly compare the OTS and the ANS, we find that they have a number of shared features. They are both core systems. They are innate. They are independent of language. They're both pre-verbal or pre-symbolic. They occur across many human cultures and across many animal species. And I will assert that neither is a number system. We know that's the case for the OTS, but I will claim that that is also the case for the ANS. Now, they contrast in the following ways. The OTS is capacity limited, ANS is unlimited. OTS is precise, while the ANS is approximate and noisy. OTS is primarily visual spatial, while the ANS is multimodal. OTS is relatively stable over the lifetime, whereas the ANS sharpens over the lifetime. There have been a variety of attempts to account for the relationship of the OTS and the ANS. There is a single system view by which the ANS is said to account for all of the OTS behavior, thus only one system is needed. This has been experimentally disconfirmed. There is a two-system view according to which the two systems are seen to be mutually exclusive. This has also been experimentally disconfirmed. The idea that they are complementary, in other words, that one system only comes on or prevails while the other system is disadvantaged in some way, is a contender, as is the aspect that the two systems are both present, but they are in some sense antagonistic or competing with each other. The OTS and the ANS then are the two pre-symbolic systems of numeration that young children have access to as they learn to count. The process of learning to count doesn't take place rapidly. It proceeds over an almost 2-year interval, and it proceeds in stages. Children begin as one-knowers. In other words, they understand fully what the word and the count aspect of one means somewhere between their second year and 3 years, 4 months. They proceed on to become two-knowers and then three-knowers, and often that is enough for them then to leap on to becoming counting principle knowers. In other words, they can count up the count list that they have previously learned. In a smaller number of cases, children move from becoming three-knowers to four numbers and then acquiring the counting principles. By the time they're 4.5 years old, they're typically capable of a large numerical counting. Piaget's The Child's Conception of Number was the dominant theory of how children learn to count that prevailed through the middle of the 20th century. Piaget held that children had a primitive intuition of set, and that they learned through progressive one-to-one matching of objects, but that they didn't really acquire a full concept of number until they were age 6 or 7, when they had grasped the conservation of quantity. Gell-Mann and Gallistel challenged Piaget's approach. They hypothesized that there were cognitive mechanisms that were innate to humans, namely numerons, which were preverbal representations of cardinal numbers, a cognitive linear accumulator, and an actuator that together accounted for the onset of the accounting principles. The explanation of counting that I will focus on for the remainder of the talk is due to Susan Carey, and it appears in her recent work, The Origin of Concepts. Carey refers to her theory of counting as enriched parallel individuation with Quinian bootstrapping. Let me break down what those terms mean. Parallel individuation really is nothing more than the object tracking system, the OTS. By enriched, Carey means set-based quantification, for example, the linguistic discrimination between a and some. Quinian bootstrapping is a process where a scaffolding structure such as the verbal count list, 1, 2, 3, 4, 5, for example, is placed in correspondence with the objects that are tracked by the OTS. In other words, the count list acts as a placeholder by which the child eventually learns the association between the verbal word one and the event, the cognitive event that is associated with one object, and so forth. The term bootstrapping appears in many different contexts. It appears in physics, computer science, and various aspects of linguistics. Carey attributes her notion of bootstrapping to the philosopher W.V.O. Quine, and I want to explore that a bit. She uses his chimney metaphor where he discusses the building of a chimney by the builder who uses the lower stages of the chimney to build the upper stages, climbing progressively upwards within the chimney until the chimney is fully built. Now, Quine also uses several other metaphors that he derives from Wittgenstein and from Neurath. Wittgenstein had a ladder metaphor, the idea that one used a ladder as a scaffold device to make a transition from one level to another, and having achieved that transition, the ladder then is pushed away. Neurath talks about building a boat while at sea, or repairing a boat, having to replank it and stay afloat while being in the middle of the water. The bootstrapping metaphor needs to be looked at a little more closely. What really is the compelling aspect of the term bootstrapping is its impossibility. It is literally impossible for a person to lift themselves up by their own bootstraps. And that gives the power to the term itself. What needs to be considered, though, is that bootstrapping is quite possible, a very doable prospect, if we bring in a second dimension, an unexploited, unused dimension prior to the bootstrapping event. For example, in the literal physical sense of bootstrapping, if one used a rope and a pulley system and tied that to one's bootstraps, one can easily pull oneself up. So what was miraculous is very simple physics. What I would like to suggest this in terms of the cognitive use of bootstrapping is that bootstrapping is the integration of previously separate cognitive dimensions or processes. From the perspective of the foregoing, I would like to briefly revisit cardinal number counting. I'm going to assert that there are three pre-symbolic numerative processes. One, a set binding process. Now, this is a process shared by both the OTS and the ANS. Then there is an individuation process that is primarily associated with OTS. And then there is an ordering process that is largely concerned with the ANS, or what might be a general magnitude system. There is also, in addition to these pre-symbolic process, one symbolic language process, the verbal count list. The integration of these three processes enables cardinal number counting to proceed. I would like to point out that language provides the entry point for cultural difference and the opportunity for metaphor. Now, Carey's theory of cardinal number counting emerges from a more general theory of conceptual change, and I'd like to review that for just a minute. Carey's basic ideas here are that one starts with a simple conceptual system 1, and then by using a placeholder and bootstrapping processes, one arrives at a conceptual system 2. And this is seen in a variety of actual historical examples, for example, in the conceptual changes in science. Carey cites Kepler's theory of planetary motion, Darwin's theory of evolution, and Maxwell's theory of electrodynamics as various historical examples of how conceptual change actually proceeds by bootstrapping processes. This is sort of an embellishment of Kuhn's notion of paradigm shift, where Carey is actually going in and looking at the cognitive processes that are involved in a rapid transition, a discontinuous transition from one paradigmic level, say conceptual system 1, up to a second discontinuously obtained conceptual system 2. I would like to use Carey's more general theory here now to look at the historical example of imaginary numbers and apply this notion of conceptual bootstrapping back to it. And not only do we see something about Carey's theory in the larger sense of conceptual change, but what is learned then is turned back to learning more about the pre-verbal conceptual processes that are available for acquisition of counting. The possibility of imaginary numbers appeared about 2,000 years ago when Heron of Alexandria noted that it was possible to consider the square root of a negative number, namely the square root of -1. But the mathematical utility of imaginary numbers did not appear until the 16th century, when Italian mathematicians used them to solve cubic and quartic polynomials. It was another century before they were given a name. Descartes called them nombres imaginaires, and what he meant by that was not complimentary. He was basically disparaging the notion, although having to recognize that imaginary numbers certainly were useful. It wasn't until the early 19th century, with separate discoveries by Wessel and Argonne, that the imaginary number can be put on a much more mathematically acceptable and understandable conception. The problem with the imaginary number is that it cannot be found anywhere on the real number line. Nowhere does it make an appearance, and so what is it? By implementing a second dimension, Wessel and Argonne found that one could reconceptualize the imaginary number as, in fact, a process, an operation. By multiplying by I, namely by the square root of -1, one could rotate the real number line up into a second dimension, the imaginary dimension, and therefore mathematically describe what it is and where it is and how it operates. A second application of I then proceeds with a rotation back down to the real number -1. With this, a great deal of comfort in the conceptual process of the imaginary number was obtained. It's really important to step back a moment and see what has happened here. The mental number line has gone through a rotation, a mental rotation. And this is a phenomenon, this type of mental rotation has been studied extensively over the past 30, 40 years. There are some classic studies by Shepard and Metzler that show that when an object is mentally rotated, whether it's a perceptual object or conceptual object, that the time that it takes to rotate the object through a specified angle lengthens as the amount of that angle, the degree of that angle lengthens. In other words, it's as though the perceptual or conceptual object is actually physically rotated in some sort of conceptual space. Okay, now the neural basis for mental rotation is under current study, and mental rotation occurs in the ventral caudal portion of the intraparietal sulcus, and it also associated with the superior parietal lobe. And these are regions that are also well associated with the various prenumerative processes that we've discussed previously. Considering what we've just learned, I would like to go back and once again summarize the core processes involved with pre-symbolic numeration. I will assert that there now are reason to believe that there are 4 distinct pre-symbolic numerative processes. They were, as before, set binding, the distinguishing process of the OTS, the ordering process of the ANS, and now there is a rotation process. So all of these processes are innate, they're genetically based, they're characteristic of Homo sapiens in general. They're also present in other species, and they can be seen and argued to enhance the survival of the species. They also show the integration which is needed in order to develop the various number systems that humans have come up with. And they also show a dependence on culture, language, and education. We've arrived, however, at a point where we have to ask, how is this possible? How is it possible that there are dedicated neural regions available for counting that are available on such a short human evolutionary time scale? Now, N has answered this with a hypothesis called the neuronal recycling hypothesis. And he suggests that these concepts of mathematics have had to squeeze themselves into the brain by invading cortical territories dedicated to closely related functions. Thus, the arithmetic capabilities invade the nearby areas for coding of space and eye movements. In the foregoing, we've covered a great deal of territory. Clearly, there has been much learned about counting, how it is that humans learn to count, but clearly as well, there is much more to be done to clarify how counting cognitively proceeds. Thank you.
Thanks again for your interest in this presentation. Please email me if you wish to discuss any of the points I've raised.